Okay, so we are finally ready to express the quadratic approximation of a multivariable function in vector form. So I have the whole thing written out here where f is the function that we are trying to approximate, x naught, y naught is the constant point about which we are approximating, and then this entire expression is the quadratic approximation, which I've talked about in past videos, and if it seems very complicated or absurd or you're unfamiliar with it, and just dissecting it real quick, this over here is the constant term. This is just going to evaluate to a constant. Everything over here is the linear term because it just involves taking a variable multiplied by a constant. And then the remainder, every one of these components will have two variables multiplied into it. So like x squared comes up and x times y and y squared comes up. So that's the quadratic term. Quadratic. Now to vectorize things, first of all, let's write down the input variable xy as a vector. And typically we'll do that with a bold-faced x to indicate that it's a vector. And its components are just going to be the single variables x and y, the non-bold-faced. So this is the vector representing the variable input. And then correspondingly, a bold-faced x with a little subscript o, x naught, is going to be the constant input, the single point in space near which we are approximating. So when we write things like that, this constant term, simply enough, is going to look like evaluating your function at that bold-faced x naught. So that's probably the easiest one to handle. Now the linear term, this looks like a dot product. And if we kind of expand it out as the dot product, it looks like we're taking the partial derivative of f with respect to x, and then the partial derivative with respect to y. And we're evaluating both of those at that bold-faced x naught input. X naught as its input. Now each one of those partial derivatives is multiplied by variable minus constant number. So this looks like taking the dot product here. I'm going to erase the word linear. We're taking with x minus x naught and y minus y naught. This is just expressing the same linear term but as a dot product. But the convenience here is that this is totally the same thing as saying the gradient of f. Gradient of f, that's the vector that contains all the partial derivatives, evaluated at the special input, x naught. And then we're taking the dot product between that and the variable vector, bold-faced x, minus x naught. Since when you do this component-wise, bold-faced x minus x naught, if we kind of think here, it'll be x the variable minus x naught the constant, y the variable minus y naught the constant, which is what we have up there. So this expression kind of vectorizes the whole linear term. And now the beef here, the hard part, how are we gonna vectorize this quadratic term? Now that's what I was leading to in the last couple videos, where I talked about how you express a quadratic form like this with a matrix. And the way that you do it, I'll just kind of scroll down to give us some room. The way that you do it is we'll have a matrix whose components are all of these constants. It'll be this 1/2 times the second partial derivative evaluated there. And I'm just gonna, for convenience sake, I'm gonna just take 1/2 times the second partial derivative with respect to x, and leave it as understood that we're evaluating it at this point. And then on the other diagonal, you have 1/2 times the other kind of partial derivative with respect to y 2 times in a row. And then we're going to multiply it by this constant here, but this term kind of gets broken apart into two different components. If you'll remember in the quadratic form video, it was always things where it was a and then 2b and c as your constants for the quadratic form. So if we're interpreting this as 2 times something, then it gets broken down, and on one corner it shows up as f xy, and on the other one, kind of 1/2 f xy. So like both of these together are going to constitute the entire mixed partial derivative. And then the way that we express the quadratic form is we're going to multiply this by, well, by what? Well, the first component is whatever the thing is that's squared here. So it's going to be that x minus x naught. And then the second component is whatever the other thing squared is, which in this case is y minus y naught. And of course, we take that same vector, but we put it in on the other side too. So let me make a little bit of room, because this is going to be wide. So we're going to take that same vector and then kind of put it on its side. So it'll be x minus x naught as the first component, and then y minus y naught as the second component, but it's written horizontally. And this, if you multiply out the entire matrix, is going to give us the same expression that you have up here. And if that seems unfamiliar, if that seems, how do you go from there to there? check out the video on quadratic forms, or you can check out the article where I'm talking about the quadratic approximation as a whole. I kind of go through the computation there. Now this matrix right here is almost the Hessian matrix. This is why I made a video about the Hessian matrix. It's not quite, because everything has a 1/2 multiplied into it. So I'm just going to kind of take that out, and we'll remember we have to multiply a 1/2 in at some point. But otherwise, it is the Hessian matrix, which we denote with a kind of bold-faced H, and emphasize that it's the Hessian of f. The Hessian is something you take of a function. And like I said, remember, each of these terms we should be thinking of as evaluated on the special input point, evaluating it at that special, bold-faced x naught input point. I was just kind of too lazy to write it in each time, the x naught, y naught, x naught, y naught, x naught, y naught, all of that. But what we have then is we're multiplying it on the right by this whole vector is the variable vector bold-faced x minus bold-faced x naught. That's what that entire vector is. And then we kind of have the same thing on the right, bold-faced vector x minus x naught, except that we transpose it. We kind of put it on its side. And the way you denote that, you have a little t there for transpose. So this term captures all of the quadratic information that we need for the approximation. So just to put it all together, if we go back up, when we put the constant term that we have, the linear term, and this quadratic form that we just found all together, what we get is that the quadratic approximation of f, which is a function, we'll think of it as a vector input, bold-faced x, it equals the function itself evaluated at, whatever point we're approximating near, plus the gradient of f, which is kind of its vector analog of a derivative, evaluated at that point. So this is a constant vector, dot product with the variable vector x minus the constant vector x naught, that whole thing, plus 1/2 we'll just copy down this whole quadratic term up there, the variable minus the constant multiplied by the Hessian, which is kind of like an extension of the second derivative to multivariable functions. And we're evaluating that, we're evaluating it at the constant x naught. And then on the right side, we're multiplying it by the variable x minus x naught. And this is the quadratic approximation in vector form. And the important part is now it doesn't just have to be of a 2-variable input. You could imagine plugging in a 3-variable input or a 4-variable input, and all of these terms make sense. You take the gradient of a 4-variable function, you'll get a vector with 4 components. You take the Hessian of a 4-variable function, you would get a 4x4 matrix. And all of these terms make sense. And I think it's also prettier to write it this way because it looks a lot more like a Taylor expansion in the single variable world. You have, a constant term plus the value of a derivative times x minus a constant, plus 1/2 what's kind of like the second derivative term, what's kind of like taking an x squared, but this is how it looks in the vector world. So in that way, it's actually maybe a little bit more familiar than writing it out in the full, component by component term, where it's easy to kind of get lost in the weeds there. So full vectorized form of the quadratic approximation of a scalar-valued multivariable function. Boy, is that a lot to say.